Hello students, let us discuss Fourier transform today. We have already completed Fourier series and we have seen uh, Fourier series is basically superpositions of different harmonics. So if you see the Fourier series, a complex Fourier series expansion of a function, we see here you have n omega 0. So this n omega 0 forms different frequencies. And this n varies from minus infinite to infinite. That means the frequency spectrum of the frequency spectrum for periodic functions expanded by a Fourier series is discrete because there is a limited time period. So there is only limited frequency by which we can form that function. Now, Fourier transform is applicable when your function is non-periodic. So your Fourier series is applicable when function is periodic. Fourier transform is applicable when function becomes non-periodic, and this is basically a continuous frequency spectrum. Here, your frequency spectrum, if I draw different frequency component, that is discrete, but Fourier transform is a continuous frequency spectrum. So what happens if I increase this time period t? Okay, if so, this is the box function whose Fourier series I have already written here. We calculated in last class. So now as t increases, t goes to infinite, this periodicity vanishes. Now you have only one function, one box, which is not periodic. That means this is a now if I want to write a Fourier series for this function, when t goes infinite, what will become? This difference of these frequencies, difference between frequencies n omega 0 and minus n minus omega 0, that will be equal to omega 0. And because t goes infinite, that means this difference will become continuous. So I can replace this n omega 0 by omega, a continuous variable, in the Fourier series. So let us see what happens. So if my t goes large, so I have frequency ft, which is n minus infinite to infinite Cn e power iota n omega 0 t, whereby Cn are defined as minus t by 2 to t by 2 ft e power minus iota n omega 0 t dt. So now plug back this Cn value in this expression of ft. So my ft becomes n minus infinite to infinite. Cn is 1 by t minus t by 2 to t by 2 ft e power minus iota n omega 0 t dt. Okay. And here you have e power iota n omega 0 t. Okay. Now your t is 2 pi by omega 0. So I replace this by 2 pi and omega 0 I bring here. Now if t becomes infinite, then this summation becomes continuous. If this is become minus infinite to infinite, 1 by root 2 I break in root 2 pi, 1 upon root 2 pi minus t becomes infinite. So this become ft. And when t is infinite, this become continuous. So I'm writing this is a iota omega, and omega I'm replacing my omega t and your dt. And then you have here e power omega t. This becomes d omega 0 continuous. Omega has become d omega 0 difference. Now this is continuous, and this function I can write ft as 1 upon root 2 pi minus infinite to infinite f omega e power iota omega t d omega, or omega 0. You write d omega only, d omega. So now my f omega becomes 1 upon root 2 pi minus infinite to infinite. What is my f omega? This is my f omega. Okay, that is 1 upon root 2 pi ft e power minus iota omega t dt. Okay, this is called Fourier transform. Fourier transform, or ft, simply ft. And inverse Fourier transform, we have already seen. This is 2 pi minus infinite to infinite f omega e power iota omega t d omega. Now these two integrals form a pair. One is Fourier transform, other is inverse Fourier transform. Now there is nothing special about this factor 1 upon 2 pi. There are alternative approaches to write these integrals. So generally this way of writing, because we have both 1 upon 2 pi in both integrals, so this is symmetric way. But many branches like in data electronics, signal processing, you define Fourier integrals in different ways. So there are different alternative approaches. So these alternative approaches are, this is the one approach, and second approach you can write, you can define f omega by simply minus infinite to infinite ft and omega t dt, and you can define Fourier transform ft as 1 upon 2 pi minus infinite to infinite f omega iota omega t d omega. Sometime third approach, you can put it 1 by root 2, 1 upon 2 pi coefficient here, and this you can make it 1. This is a third approach. There is a fourth approach also, where instead of omega you write the frequency here, and this become minus ft minus omega t, omega you write 2 pi nu t dt, and here ft becomes f nu e power iota 2 pi nu t d nu. Okay, that 2 pi is used inside the omega because omega is 2 pi nu. So omega by 2 pi nu, so that can be put it inside. So these are different ways of writing Fourier transform. And next class we'll solve some problems and we'll see what is the properties of Fourier transform. So I'll stop here. Thank you.